Hello, everyone. Welcome to our live stream. My name is Baz Barami from Wolfram Research. Today, is going to be our second session that we are discussing about the spread of, infectious diseases using compartmental models. In the previous session, we started with a very simple one. We explore, its feature. Uh, that model is mostly applicable for one small region with no interaction with the surroundings. Today, we are going to see how we can extend that model to describe a much more complicated cases, such as the spread of a virus throughout the country. Uh, uh, my guests are Anton, as yesterday, and also we have another guest, Diego. He will help us with, modeling of the United States. Handing it over to you, Anton.
Thank you, Mats, for the introduction. In this session, we are going to consider an extension of the standard compartmental epidemiological models. And this extension is going to be through scaling of those models at different sites. This here is a visual aid. As I mentioned in the lecture session yesterday, in most cases, when you have cities or densely populated areas which are separated, say within a country, which is the case here, the usual assumptions about the compartmental models do not apply. And because of this, it's a good idea to consider a possible scaling through space. And so in this session, I'm going to describe how this is done in the following steps. I'm going to show some, actually I'm going to show an example very quickly. Then I'm going to briefly describe what is the algorithm, the description of the algorithm. We're going to see two concrete examples with random graphs and with specialized grid graph. And while I'm explaining the algorithm, I'm going to be using some simple two-side complete graph. All right, so what is the example I was talking about? Well, let me go through this grid graph. So we can see here, I just need to open this graph. Imagine my country is connected in this way. My country has these cities between 1 and 84, and you can see that nobody is coming to city number 1. Everyone is traveling away from city number 1, and nobody is leaving city 84. Everyone goes to that city. So the question is, and you can see all these directions of travel. They point all of the directions horizontally, and point in the same direction to the left, and all vertical directions point up. So we basically have obviously some kind of flow in this direction. So if I want to make a simulation of how the certain virus or viral disease is going to be distributed across this artificial country, one way to do that is with the model I'm presenting, and here we can see the simulations and more. I'm going to this is just a teaser. And here, for example, is an animation which shows how the infection distributed from the first city throughout all of the cities and died off.
All right. As you can see, it's like a wave, just, for our audience, starting from, one side, a wave of, virus goes from one side to the other side.
Yeah, this is definitely a wave, and it's a very good observation. One of the things we can say, also see for this wave, but the front is, we have more of a contrast in the front than to the tail, and this is something to be expected if we look into the how this plots, infectious plots develop in time. They actually have a steep starting curve like this one here, and then we have this long tail. So, all right. So, what is exactly the approach? It's fairly simple. I do have. I contracted the whole network. Let me expand all of it. First of all, before explaining the theoretical prerequisites, I would like to mention that there is a dictionary here. We have a single site The single site is something we discussed yesterday. If I just as a reminder, this is the type of models we have, like say for a single site, and this is an attempt for doing a fitting. So I have a certain model, like say Sayer model on a single site, and I want to do to distribute this model across a network of sites. And this multi-site area, it has multiple sites, and then we have we know the traveling patterns between those sites. The algorithm here, which I'm going to be describing, MCEMEA, stands for multi-site epidemiological model extension algorithm. I'm just going to call it the multi-site algorithm. There's a certain theory behind this. Basically, we look into if we take, say, the equation for the susceptible population, which is the standard equation from the SIR model, we simply extend that equation with birth terms, which come from traveling, and death terms, which come from a departure. So I'm not using some death rates or birth rates. I'm using the actual traveling fractions rates. This K, A, B, it tells me how many people traveled from site A to site B, and KBA tells me how many people traveled from site B to A. I chose the letter K because this is more or less a contingency matrix derived from the source destination pairs or source destination traveling records. So you can see that this is basically the same as a death term, and this is the same as a birth term. Now, we need to be careful when we put this kind of terms in the equations, because we want to make sure that these terms, they do not exceed the number of people in the corresponding site. So I have put this assumption here. In the actual code, there's some guards about this, and so this is taken into account. This is a visual aid. It's more or less what I've been describing in several ways. I'm taking the model, say like SIR or anything else, and I make multiple copies of this SIR model across my graph. And then using the patterns, traveling patterns within this graph of sites, I do this extension, what is given here. So after I do that, I combine the ordinary differential equations systems of all of these models. I combine them into one big one, and then I'm solving this big system.
Let me just comment very briefly. So there are two big challenges here. How we should describe the interaction between different regions, which is basically very similar to the graph that you see here. This is the case of only 4 sites. But the very big question, the next challenge would be, what are those interactions? For example, K23, the traveling patterns. So today, we are going to discuss about this model, assuming that, we know the information about traveling pattern. And then at the very end, and more in detail next time, we are going to discuss these traveling patterns, for example, for United States. And then if we apply, this model for United States, what's going to be the result?
Yeah. Thank you, Matt. Very, very good, very important clarification. And yes, apparently I'm staying more on the cleaner theoretical part. And the purpose of this notebook is just that. I'm not doing much real data here, actually not at all. It is just to explain the methodology and use some kind of standard graphs to show how this can work. Although I have been using random graphs, and the random graphs should be very close to a real situation, to modeling a real situation. So
let me remind our audience, there is a link, we already pasted that link on the chat channel, so you can download this notebook, which has been published on the Wolfram community website.
Yeah, yes, I did it this morning. All right, so this single site model, I mean, very, very simple, but what is happening here is, because I mentioned that a crucial step of this multi-site model is to make multiple copies of the single site model. This is what is being demonstrated here. This model here, model 1, which I have generated through a package I have written just for this type of models. I have a function add model identifier, and I can, add a model identifier, and then I have a copy of this model. If I put something else, like say 1, obviously, it can be taken. I'm having another copy. In my examples below, I just use integers, like this. All right. So what is happening here? I'm going to describe this with a two node graph, because it's easier to follow, easier to display the results, intermediate results. So I have these 2 sides, and I have made this random matrix, which tells me the traveling patterns between the 2 sides. You can see that there are much more people traveling from site 1 to site 2 than from site 2 to site 1. For whatever reasons, I have decided that this is my traveling patterns matrix. Then I am again taking just for completeness in this of the computations as a workflow in this section. I'm making my single model. I'm making my big model here. So the function here knows how to make multiple copies of the single model I have taken, and here I have mentioned the populations for which I want to change the equations. So here, when I was describing the theoretical part, I was saying that I assumed only we're assuming here that only the susceptible population has traveled. That's not necessarily, obviously, it doesn't need to be the case in general. We might think that everyone is traveling, susceptible, infected, exposed. In this particular case, though, in this particular model, because my SAIR model actually does have 2 populations, that's why it's called, the name of this model is SEI2, because I have two infected populations, normally symptomatic and severely symptomatic. So for this model, I let the normally symptomatic people would be traveling. They might even not know, let's say they have the coronavirus, and the severe ones, they don't. So here I have specified which populations are going to travel, and then I have changed the equations accordingly. These are all of the equations now I have in the model. This model, big model, I have joined the equations from the individual sites into one, and I have changed them in such a way that I have this birth and death terms derived from traveling patterns. If I remove, say, one of these populations, like say the exposed population, we should be able to see how the exposed population does not have these terms anymore. All right, so let's actually return to the previous part here. We're just showing the different populations in the model. Actually stocks, not populations, because you'll see here there is something called MLP. This is the money from lost productivity. So this is the money loss tracing. We're just solving the equations here, and we display the equations. Oh, sorry. So yeah, and is this something we expect? Well, yes, it is, because as I mentioned from the beginning, I have much more people traveling from site 1 to site 2. And so, yeah, this linear decrease I see here of the population of site 1, yeah, they're leaving site 1. And I'm seeing also increment of the people who are going to site 2. So this all makes sense, and all of what I see here, it does adhere to the typical patterns we would see in the single site models. All right, well, what is going to happen if, instead of using a constant matrix here, obviously in a real life situation, I might want to use some time dependent, some function which approximates in time what are the traveling patterns. And so this is what is happening here in this section. I'm just, the steps are exactly the same. It's just instead of constant terms here, I have put, I have these terms which are like time dependent. So you can see some oscillation here. Doesn't need to be oscillatory. It can be something else. It can be some other, time dependent function derived from some data analysis or some kind of predictions or forecasts about the travel after, say, we know that certain outbreak is in place. So then after, because of this oscillatory, or like I'm using ups sign, so it's not exactly oscillatory, but because of this nature of the signals, I actually, when I make the simulations, I would expect this to be reflected in the final results. And it is. I mean, you can see how these oscillations they have been reflected in the final results. And we have, again, the similar pattern which we saw from above. So
just quick comment, like, on those graphs, the main reason that we are not including the death is that, it can be easily derived from, infected population. So it has somehow independent from other dynamical equation. That's why, we are not showing that.
Yeah.
But if somebody is interested, they can easily get it.
In the previous, that's a good point. In the lecture yesterday, I was actually saying that one of the ways to extend the models is to give def equations, like something like this. For example, if I want to extend the equations of my core model before making the scaling, the multi-site version, I mean, I cannot this def equation here. It's very simple. I have the def rate multiplied the def rate which I have from the infected people, and severely normally symptomatic and severely symptomatic. Now I'm not tracking the usual deaths. The deaths from the other populations are not tracked here. So this particular equation, what you see here, it's only tracking the deaths from infections. All right. So I mean, I'm saying that we see results which are expected, and but we actually do need a much better proof. And one of the ways to do that is to actually see how this to use a simpler graph, simple but large graph, and we see some kind of macro quality which we'll expect. This is the wave we did see in my teaser, like say 12 minutes ago. And so here, this is what is happening, what I'm going to do next. I'm going to use constant traveling patterns over a grid graph. My grid graph is specially constructed, as I said, to be all the edges to kind of to go in more or less one direction. So there's a general flow from the bottom node, from the first node to the largest node. And so when I make my constant matrix, this is how it looks like. So here we see from the summaries that the non-zero elements, they all have the same values. And I have scaled, again, I'm using a single model. I am scaling it here. And I'm going to explain the initial conditions, but here we actually, after we have set the initial conditions, selected the initial conditions, solve the system, this is this is our results. And we can see that, generally speaking, for the lower index sites, the evolution of this infections, recovered and susceptible populations happens earlier, right? So the higher indexed sites, this happens later in them. And this is why is this? Well, I have put all my populations to be constant, to be 1 million. All of my populations all of my sites have only zero infected people except the first one. The first one has a severely symptomatic person who is infected, and because he's severely symptomatic, I guess it was detected. If he was normally symptomatic, people might think, in case of the coronavirus, they might think it's just the standard flu or whatever. So I have changed my susceptible populations accordingly. So I have for all of the susceptible populations at all sites, they equal the total population except for the first one, in which we have the population of the total population minus the one who is infected. All right, so now what I'm saying is that I should be expecting, if I infect one person here, this person to start infecting other people in site 1, and then because of the traveling patterns, that infection to spread out. And more or less, this is what we see with these plots. If I do, let me reevaluate this plot. If I here, this was just a random sample of nine sites. But if I plot the first and the last sites, what is happening for them, you can see that how the total population of the first site decreased, and this is to be expected because nobody is traveling to the first site, and the total population of the last site increased because people just go to it. But even if people left, my point is, but this what we see here with the first site definitely fits our expectations. All right, so how we can actually see the evolution of this different populations? One way to do that is to, this is the evolution of the total population, but what you see here, it's I'm producing the sum of the infected, severely symptomatic population and the infected normally symptomatic population. And so we can see this wave, and I have taken certain step here just to kind of for brevity of the exposition. But let's look into the animation here. This is the same data, and now if we run the animation, we should start seeing how from someone being one person being infected in site one, how this propagates throughout the entire network or graph of sites. This is actually showing fairly, it's demonstrating fairly decisively what our model works. Because we have seen that in each individual site, we see the typical patterns for the standard single site model. We have taken the CEI2R model, and then we actually do see the propagation of the wave of the infected populations. Now, let me try to change this into, say, just exposed population. The reason I'm going to do this experiment here is that I actually want to show that with the exposed population, my wave is going to be tighter. And so, if I shouldn't take long, yeah. So you can see how this wave is much sharper or much tighter, right, compared to the infectious wave. Again, again, this actually does make sense if we look at these plots here, like say for the first site or any of these sites, the exposed population. This is the one here, right? It has a much sharper form profile than the infected ones. And so again, this is again to kind of build confidence in the model we have. All right, so I'm going to, there's another interactive interface here. Let me just collapse this. If you want, you can see all of the populations probably all together. I'm not
just one quick comment, because some of our users, they already ask a few questions regarding like how these models would represent the actual data. At this stage, what we are doing, we are basically playing with some toy models, okay, in order to see like the algorithm that we have is working, and to understand and analyze the underlying dynamics. Okay, and then, because as said at the very beginning, the biggest challenge is that how we would explain or describe the interaction between different sites. So that's a big challenge, and that's the topic that we are going to discuss next time. But having said that, all of these models, we have to be very cautious to see them as some models providing prediction. So this is not basically our goal here, and we have to be very, very conservative about that. Anton, would you like to comment on that? How people should see these models, because I know many people, they would like to see some forecasting, like how these models provide some forecast. How should be our stand toward this idea of forecasting the spread of virus?
So right, well, there's this random graph model, it's going to be explaining, probably it's going to be closer to what is happening in a real situation. What I want to mention though, so in a sense, right, I mean, if you can do simulations with a random graph and whatever random time dependent matrix, or which describes the traveling patterns, this means that you can do it with real data. And now the question is, with your real data, do you know the traveling patterns? What is going to be included in those traveling patterns? Is it just, say, flying by air, or if some of the sites are close enough in proximity, you might consider traveling, say, by rail or by car and so forth. Another thing to discuss here is that, let me actually show this in some other plot. So when we evaluate these solutions, right? So we actually, what we saw with the previous in the previous lecture with this single site models, right? I mean, there's certain profiles here which are in the real data, which are cannot be easily approximated, cannot be easily fitted through calibration. But if I plot my data for this grid graph, for example, if I try to plot the results from what I have here, and let me just do quickly readjust here the numbers. Then the numbers here, say, for the infected and for the affected population. So here the one which is from the grid. So I mean, you can see that all of this are pretty sharp, right? Meaning they have the usual profile we expect from this kind of models for all this 84 sites. But if I do the sum of these models, right? So if I take, let me see what is going to be this here. If I take the values of this structure, and then if I do total, and just do standard application, I mean, you can see that I have a very different distribution. It's not as sharp as here. It's actually very likely to be a type of distribution like what we are seeing in real data. This means that in this real data, actually the spatial component or some of the other parameters might be in play. So that's why the simple models didn't work. So this extension through space, it is a important ingredient. It can be used, and it is a non-trivial. It's not trivial. It cannot replace it with other modeling approaches. You need to do some kind of special distribution of the populations. But then, how do you build confidence that this is actually working? So we're going to do the simulations incrementally. We describe the theory, discuss the theory. We actually produce certain easy to perceive, easy to predict tests of what is the behavior of the overall system and how it's going to be simulated. We make the simulations, and if we see that the simulations coincide with the behavior we expect, we decide that this model is adequate, and then we need, or if we want, we can apply it to real data. This is the application to real data is going to be happening in the next section. In order to be sure or kind of build further confidence that this can be applied to real data, this is why I have been using random graphs. So with the random graphs, we can actually, we have different distributions, whatever, and so we with this different distributions, the sites and the traveling patterns between them. If we see that the system is working and it's producing results which make sense, then we're saying, okay, we are actually prepared to do this in a real situation. This is more or less almost, I think at this point is this is everything I wanted to discuss, except there is one element here. My goal is not just to make a better prediction models from the typical setup of epidemiological models. I do actually want to include the economics component and how the economics of the situation is going to influence the propagation of the disease. And so that's why in my simple model, I do have a money kind of equation. This is the money loss from productivity equation, and I am able to follow it and see what is happening with it. The extensions, the further applications of this algorithm, they're going to be together with more comprehensive models on a single site, more comprehensive models, which include larger economical topics or perspectives of what is going to be happening in the single sites. So I think I think this is more or less what I wanted to.
So I guess, Anton, he provide, a very detailed, description. Let me re-emphasize that, whenever we want to model a very, very complex phenomenon, such as the spread of a virus through a country, we should start with some simple models. That's how, this is the scientific approach. We start with a simple model. After we make sure that, that simple model can reproduce some simple situations, step by step, we make it more and more complicated. And through each step, we have to test our extension using some toy models. That's why, we started some grids. We are well aware that, those grids, for example, that very simple one that Anton showed, they do not represents any realistic situation. We know that. So why, we are studying, those graphs? Simply because we want to be sure that our scaling up is working. That's the only way that we could understand what are the features that, are predicted by this model. And after we were tuning all the, nuts and bolts of, this, complex model, we can apply it for a situation like any country, United States. Now, in order to do that, those segmentations, they are not easy. We may say that, okay, let's apply, this model for United States. Then the big question is that each site that we have on that graph, they represent what? Do they represent a city? Do they represent a state? Now, a very big question is how we can do some segmentation on the top of a country and then apply our graph model. So this is the topic for the next time. But before wrapping up, this session, I would like to hand over, our discussion to Diego, who has done some very nice segmentation. I would like him to share his screen and give us some insight about, what we are going to discuss next time.
Thank you, Matt. So once Anton provides, let me share the screen. We can.
I should stop sharing.
Yes, please. Thank you, Anton.
Mm-hmm.
All right. So Anton has built a very robust set of packages, which we will take them to the next step in the following session. In the next session, what we will do is we'll take the United States, and we're going to start with a simple model that we can then in the future build up. But just to give you a teaser, what we have done with the Anton's model is take it to dividing the United States into main airport hubs, more or less of a 50 kilometers distance between each other. We will show the different tools and the different issues that we had along the way dealing with real data and how to use that data and analyze it. And finally, set up the different mobility of air travel between the different sections of the country where the data is easily available and what were the challenges around it. building this graph that we discussed between the different nodes or airport hubs and the transportation between the different cities or grids, and then using the CEIR2 model, start using this to try to gain insight from a qualitative level of what the impact is of the transmission of a epidemic across the country, initializing it, for example, in the Seattle area, and how it will distribute across the main airport hubs of the United States and then go itself through the country. And then we will, which is not finalized yet, is use the look at one node and start doing further analysis and how that compares, for example, or fits a curve like what we have observed in Italy. So that's a little teaser and a comparison of other countries, for example, to on daily rates of infection. Let me hand this back to you, Matt.
Thank you, Diego. Very interesting. Okay, so I guess, we could wrap up our session. As I mentioned, we explore computationally how we can model the spread of an infectious virus through a large geographical, area. And next time, hopefully we would implement this idea for United States. Thanks for watching. Have a wonderful day.